Okay, so in this section, we're going to be discussing a method of integration that is going to build on the techniques that we have so far. So at this point, really the only way that we have to evaluate integrals is to use the antiderivative formulas that we learned previously. So we're going to kind of build on that and come up with an integration technique that is essentially the reverse of the chain rule from differentiation. So just to kind of refresh our memory about how the chain rule works, we have here the formula for the chain rule that says if we want to take the derivative of the composition of two functions, so f composed with g of x, then that derivative is going to be the derivative of f of g of x times the derivative of g of x. Oftentimes we'll think about it in terms of inside and outside functions. So if we were to consider f our outer function and g our inner function, since they're being composed together, the chain rule states that the derivative of the composition of these two would be the derivative of the outer function with the inner function still inside times the derivative of that inner function g. So real quick, we could also think about this in terms of another notation that I think is going to be helpful as we move on to the substitution method. So f prime, g prime, that's a notation we tend to start with. Alternatively, what if we were to consider this and let g of x be represented by the variable u? So we're just going to try and clean this up. So this means that if we were to take the derivative of g, essentially what we would have is we would have u prime, the derivative of u. All right, so we're just doing a change of variable here. If we were to do this, think about how this changes our derivative formula. Then this would mean that the derivative with respect to x of f of now u would be f prime of this function u times u prime. So this is just an alternate way that we have to describe the chain rule. Real quickly, let's do an example from Calc 1 of the chain rule. So we've got f of x is equal to the sine of 4x cubed minus 5, and we're asked to find its derivative. Well, let's go ahead and start doing this u step that we covered right here. So what I'm going to do is I'm going to consider this to be my inner function. This is the function that's within the sine function. So we think that might be a good choice. So I'm going to call u 4x cubed minus 5. Now what this leaves us with is now we've got f of u is going to be the sine, of u. So in place of that 4x cubed minus 5, we've replaced it with u. Now this rule that we just set up here tells us if we want to take the derivative of f of u, it's going to be f prime of u times u prime. So let's get each of those. Well, f prime of u is just going to be the cosine of u, so it's just the derivative of the sine. And u prime, the derivative of 4x cubed minus 5, is just going to be 12x squared. So with these two forms, we can now conclude that the derivative with respect to x of the sine of 4x cubed minus 5 is going to be equal to f prime of u, which is cosine of u, times u prime. And if we fill in our blanks here, we've just got the cosine of 4x cubed minus 5 times 12x squared. And usually we want to put those coefficients out front. Now we've just got cosine of 4x cubed minus 5. Now, for those of you who have been doing the chain rule for a while, this might seem like we did a lot of unnecessary steps here. You'll probably be able to do this with some practice, go straight to it. I think it's important to see what goes on under the hood here, because it's going to make a nice transition into this new method for integration, which is the substitution method. So with this in mind, if we wanted to undo the chain rule, since integration and differentiation are almost like operations that undo each other, this would mean that the integral of f prime of g of x times g prime of x with respect to x is going to be the composite that we started with. So that's just going to be the integral of the derivative of f of g of x dx, which would just leave us with f of g of x plus c. And this leads to the motivation of U substitution method, is that if we have an integral that sort of matches this form right here, we could integrate using substitution. So let's see how this works. Essentially, we often refer to this as U substitution or substitution method. Essentially, what we're doing is we're doing a change of variable. We're trying to express this integral in a different variable, thus to the point where it is simplified and easier for us to integrate. So let's just say that we've got this integral f of g of x times g prime of x dx. If we were to let g of x be represented by u, and if we were to let g prime of x dx be represented by du, let's see how this changes our integral. So all of a sudden, this becomes the integral of f. I'm going to replace g of x with u, and then g prime of x dx becomes du. Now all of a sudden, we realize that, well, if we're just integrating a function, then its integral is going to be the antiderivative evaluated at u plus c. Now we originally had a function of x, and we'd like this to go back to a function of x. So let's replace that u with g of x, and now we've got the antiderivative of f evaluated at g of x plus c. So now we've got to where we need to be. So we see that this step right here, picking a u and getting a du, is going to be the crucial step in integrating this. So I realize this might seem a little bit, out of left field, some of this notation, but I think as we do a few examples, it'll a little bit more clear on how we go through this.